can try to reschedule. Okay, so as long as it's not too. Yes, yes. Just eat.
I'm kind of worried about it.
Okay, so the last couple of weeks, what we have been doing. Oh, do you guys have questions? Okay. Just add comments to one another. All right. So the last few weeks we've been looking at randomized algorithms, and we said that generally algorithms themselves are often somewhat natural, and they can be simpler than the corresponding algorithms that are deterministic. Right? So an example of this are usually quicksort. There's another classic example that we didn't do, which is min-cut. Okay. And what we said is that sometimes the analysis can be tricky. Okay, and we said, but we kind of looked at a few tools, right? So we said that often you are interested in the expected running time. Okay, so you want to say that this is the expected running time, and you want to say the probability that the runtime is large is not too high, and you want to show that it's accurate with high probability and so on. Okay. And the usual tools we use are linearity of expectation, union bounds, and so on. The other thing I forgot to mention here is repetition. Okay, so it's not really a tool; it's just common sense. But this is somehow, this is something to keep in mind. Okay, so if sometimes you might have an algorithm that succeeds with probability 1/2 or 1/10 or something. Then you just repeat it enough times, you'll get the right answer. Okay, and usually you'll have an optimization problem, so you'll know the answer when you see it. So that's another trick. Alright, so this is what we saw for the last few weeks. Then we said that okay, we've been looking at paradigms, and then we're going to look at one new one, and that's what we call linear programming. Okay, and it's part of a more general thing we started looking at last time, which is optimization. Okay. So what we said is you have some combinatorial problem. Okay, so we saw the example of independent set. And we wanted to phrase it as some kind of a numeric optimization. Then the key thing here was you've got to find what the variables are, you've got to define what the variables are. This is in some sense a modeling question. You have this combinatorial thing, you want to model it as some kind of a continuous optimization problem. Okay. And you'll have some variables, some constraints, you'll have some objective that you usually want to maximize or minimize. Okay, so sometimes there might not be an objective, you might just want to check feasibility. Okay, that's like saying, are all constraints satisfied? Can all the constraints be satisfied? So you either have an objective function or you just want to check feasibility. Alright, so this is the general theme in optimization. Okay, and the example we saw last time was maximum independent set. So this was, you are given a graph, and you want to find a bunch of vertices with the property that none of the vertices you've picked have edges between. Okay, we said, gave this example, we're looking at this example of edges being conflicts. We're going to build a team as large as possible. Okay, so find set as large as possible. Such that there are no edges. Okay, and last time you guys came up with this construction. So you're saying that okay, for every vertex, have a variable xi that's supposed to be 0 or 1, depending on whether you pick that vertex in the set or not. That's a natural way to model picking a vertex. And then you impose the constraint that for any edge, xi times xj is 0. Okay, it means, xi xj being 1 is like saying that both of them are picked. Okay, so you want that at least one of them is not picked. because in the set you picked, there should not be any edges. So this was one way to write this constraint. Another alternate way that I mentioned is that you can say xi plus xj is less than or equal to 1. Okay? And each xi isn't 0 or 1. Of course, the goal is to maximize the sum of the xi. Okay? Because the sum of xi is the number of vertices picked. And because we know independent set is NP hard, we know that solving this problem is also NP hard. Okay, so just phrasing it as optimization won't make the hardness go away. Okay, so we know that typically, optimization problems could be hard for this reason. So alright, but optimization problems are nicer. You can say, oh, okay, I'm going to maybe throw out a few constraints and hope that I get something that's easy. Right? So that's the reason we try to phrase problems as optimization. Okay, and that will be the theme of what we will see. Okay. And one thing that I didn't, so we got to this example last time, but I don't know if all of you internalized it, but you can also write problems like max3 sat and also flows, which we will see today, as optimization problems in a pretty natural way. And the key thing is, as I said, it's a modeling question. You've got to define the right variables, you've got to find the right constraints, and you want to figure out what the objective function is. Okay, so optimization problems, you can usually write it as minimizing some function of x subject to a bunch of constraints. You could write it as some p1 of x, or like g1 of x. Let's look at p1 and g1. Some of these could be equal to less than, I just wrote this for convenience. Okay, and x, I'm thinking of it as a vector, right? So x is x, so the number of constraints maybe is m and the number of variables would be m. So this is the standard form of optimization. Okay, and as we saw, not all optimization problems can be solved efficiently. And before we get there, so one way to generally think of optimization problems is what I call the geometric viewpoint, and it is what you would guess it is. Okay, so it is think of each feasible x. Okay, so a set of all x such that x satisfies all the constraints. Okay, so this is what I will, let's call it script f for this class. Okay, so just as a notation. So that's the set of all feasible x's. Okay. And this, you can view them as points in n-dimensional space because x is just a bunch of coordinates, right? X is x1, x2, x2, xn. So these are, so you have n-dimensional space, okay, something like this, and you have a bunch of feasible points. And your goal is you have some objective function whose level sets could look like this, and you want to find the maximizer, right, which is as far out in the level sets as you can. Okay. So if you don't see this thing, we'll see a concrete example. So for general functions, not that, anyway, you cannot solve it efficiently. Right? So we will see concrete examples of this in a bit. Okay, but this set of feasible points is something that's crucial. And often this is not a discrete set of points, this will be a continuous set. It will be some region that will probably look like this. And you want to optimize some function over that region. So that's usually the kind of problem we like to solve. Alright, so what is a good, so when can we solve optimization problems? So this is one question that we first want to understand, right? So firstly, do you guys think we can solve integer programs? If you've done your homework, you know you can't, right? Because like if you want your variables to be integers, Okay, so this is what also happened in this example, right? So we in the independent set example, we wanted our variables xi's to be 0 or 1. So usually optimizing, functions like this over discrete domains turns out to be quite difficult. Okay, so that's the general heuristic. Not always, but typically. Okay, so integer programs in general are NP hard. And so one general class that's very interesting is what is called convex optimization. Okay, so how many of you have you done convex optimization in your machine learning class? Yeah. Okay, good. Yeah, so all of you know, roughly speaking, what convex optimization is, and I'll just define it in a bit. But this is one pretty general example of optimization problems that you can solve efficiently. So even here there are some caveats, like you need some assumptions about the functions, but typically you can solve convex optimization type problems efficiently. So it's a general class of efficiently solving. And so this kind of method is so successful that very often you will have an integer program, or you will have something that you can't ordinarily solve, and you will try to phrase it as a convex program. Okay, and you hope that solving that convex program helps you solve the original one. Okay, and this is what I call convexification. Okay, so you try to solve a non-convex program. By the way, is everyone comfortable with the word program? Okay, so it just means an optimization problem. Okay, so it's just, if you don't, I might sometimes use words like this, but if you don't understand, please ask. So it's, so it's just a opt problem. Just due to historic reasons, these are called programs. So, yeah. So we try to solve a non-convex program by modifying it to a convex one. Okay, and of course, it won't be the solution to the actual program you want. You might get some spurious solution, but you hope that that somehow helps you solve the original non-convex program. Okay, so we'll see examples of this next class. Okay, so this is what is called convexification. Alright, so before we move on, so this is something most of you who've seen convex optimization would have seen this, but I wanted to mention it. So what is convex optimization firstly? So anyone want to define it for me? What do you mean by convex optimization? Like in this, yeah.
If there's only one minimum, so there's only a global minimum, it's finding the minimum of a convex function.
Right, okay, so you want to find the minimum of a convex function, min over f of x, where f is a convex function. And is it over the full space or over what? So usually when we specify an optimization problem, you have the objective function, you have the constraints, right? And the constraints, I said, are equivalent to defining a feasible set. Because so you have a bunch of constraints and they impose some feasible set. So what do you need about the feasible set? Can you minimize a convex function over a set that looks like this? Some hypercube or something. Because if so, I could solve an independent set, right? Because I could say linear function is a convex function. So I had a linear objective. So you need something about the feasible set. Yeah.
I mean, the feasible set should be continuous and should be just marked by boundaries and should not be discrete. Shouldn't be a discrete space.
So saying it's any continuous space. So
Which makes the, I mean, suppose we have a non-convex function, but we choose the restricted space in such a way that that space is just convex.
So you can convince yourself that if instead of the if I want to minimize something over a hypercube, so we'll see a proof of this in a bit, then minimizing over this whole box will actually find you a vertex. Okay, because you're trying to minimize a linear function. Linear functions always get optimized at the corners. Okay, we'll see a proof of that in a bit. So your argument wouldn't work there because you're essentially saying that in some sense I will find right. So what do we so what else do we need? So
It should contain the global minimum.
yeah, I mean it could there will be a global minimum, but the point is that the convex optimization as defined is basically it's minimizing a convex function over a convex set. Okay, and a convex set is simply a set which doesn't have, with the property that it doesn't look like this, where there are 2 points such that the whole line joining them is not in the set. Okay, so this is what is, so if you have not seen this, then it's not terribly important, it's not very useful for us. We'll just look at linear programs, which are much simpler. But convex optimization often refers to just this. Okay, so it's minimizing a convex function over a convex set. Okay, and convex set basically means for any 2 points, 2 feasible points, the entire line joining the points is in the feasible set. Okay. And so this is the definition of convex optimization. Okay, so you want to minimize convex function over convex set. Note that you will not be able to maximize convex functions even over a convex set. That turns out to be difficult. Okay, so that's just another thing to keep in mind. Okay, so the key is also in the minimization. Okay, and it turns out for this there is kind of a universal algorithm, and this is called gradient descent. This also hopefully you've seen in your machine learning class. I'm sure you would have seen examples of this also. There are several examples of this. And the idea is basically you have what is called the gradient of the function. So you have, this is an iterative algorithm. The reason I want to give this as an example is because the algorithm we will mention for linear programming also looks kind of similar. And the point is, most of these optimization algorithms are iterative. Okay, so you start with some solution, and let's call it x superscript 0. Then you move to a new solution x1, and so on. And after enough number of steps, you hope that you have reached the optimum solution. And all of these, you could think of them as some kind of local search. Okay, and this is local search in like a purely geometric sense. Okay, so earlier when we talked about local search, we said, oh, can I move from one solution to the other by swapping edges or doing something like this? Right? But now this is in a purely geometric sense. I am at a point, I look around, move to some point that is better than me. Okay, so this is in the purely geometric sense. And so it turns out the nice thing about convex functions is that any locally optimum solution is also globally optimum. Okay, so any local minimum is a global minimum. Okay, so property of convex function. And this is the reason you can essentially do do what is called gradient descent. Okay, and the idea of gradient descent is very simple. So you define x t plus 1 to be x sub t minus some small number which I call eta times x gradient of f at x. So if you don't know what the gradient is, you don't really have to care. So this is just an example that I'm giving you. So the gradient is one direction in which the function is bound to decrease. Okay, so you don't literally have to do the local search by checking the whole neighborhood. It's essentially one direction in which, if the function decreases at all, it has to decrease along the direction of the gradient. Okay, the negative gradient one. Okay. So this is what is called the gradient descent. So, have you guys, so in your ML course, have you guys seen proofs of why this works and so on? Okay. Yeah, so, so there's, in the spring, I keep teaching this course called Theory of Machine Learning. So there, we'll look at gradient descent for a month. We'll look at different types of gradient descent and so on. In fact, like there's places where there are courses on gradient descent. I mean, there's a whole, so there's a whole theory around it. And there's a lot of interesting ways in which you can modify this basic algorithm and you get various convergence properties. So, yeah, if continuous optimization is something that appeals to you, then this would be interesting. Okay. Alright, so but it's not appealing to us in this course, so we'll just mention this. Okay, so what I want to move on to is a special case of convex optimization, and these are what are called linear programs. Okay. And as the name sounds, this so what you have here are minimizing or maximizing, linear functions over feasible sets defined by linear constraints. Okay, so feasible sets defined by linear constraints. Okay, so this is a special case of convex programming for this reason. Okay, because it's minimizing just a linear function over some sets that are defined by linear constraints. We'll see examples in a bit, but historically this has been one of the, linear programs have received a lot of attention because a lot of problems, especially like classic problems like network flows, some kind of routing problems and so on, you can phrase them as just linear optimization, okay, as essentially linear programs. And you will have constraints that are linear. We'll actually see the examples of why flows can be phrased as linear. There are also some scheduling problems that you can phrase as linear optimization and so on. And so this is something that, in fact, if you look at the whole field of operations research, all they do is linear programming. Okay, so most of the time. So that's, so there's a lot of work on this. And this is studied since the 50s. As usual, this arose in military kind of applications, and people were doing problems like routing and network flows in those situations. And so that's when they start phrasing problems as linear optimization. Okay. And there is this very simple algorithm called the Simplex algorithm. So this is inspired by gradient descent. We'll see that in a bit. But the catch with the Simplex algorithm, it is also, it's a very natural algorithm, it's very simple to implement and so on, but there are no bounds on the running time. Okay, so that's one of the key disadvantages of the Simplex algorithm. It's very useful in practice, but we can't prove. Sometimes, or actually rather, people know examples where it could take exponential time. Okay, so it could take exponential time in the worst case. Okay, and for a long time in the 50s, 60s, a lot of people tried to come up with polynomial time algorithms for linear programming. Because it's such a fundamental problem, people didn't know efficient algorithms. And so the breakthrough came by this person called Khachiyan in 1979, and he showed that this can be solved in polynomial time. So I couldn't find a clipping, but this was apparently, this received a lot of news, and this was at a time when the Cold War was at its peak, and this Russian guy solved this problem that a lot of people had been trying to solve. Okay, so this was like, some people hailed it as like the second Sputnik or something like this, right? Because that's the first time they beat they were the first in the space race or whatever. So this was treated as such a big deal, okay, that they came up with it. Okay, so this is just to see that this is an important problem. So, alright, but now we know that linear programs can be solved in polynomial time. And here, as usual, this is in time that is poly in the input size. So in the size it takes to write down the program. Okay, so here, these kind of problems you've got to be careful. Like in the homework, you would have seen one mysterious question that says, "Why do you think it's not NP complete?" Right? So there, this notion of input size is kind of crucial. Okay, that somehow you can solve this problem in time that's polynomial in the space it takes to write down the input. Okay, because the input is now some continuous thing, right? Because you have linear functions, and linear functions you can define them by some coefficients. We'll see those in a bit, but those coefficients are just real numbers. Okay, so how do you write real numbers on a machine? And there are issues like this. Okay, so let's not get into that. So that's why I was very specific to write polynomial in the input size. Okay. Alright, so what is the canonical example of a linear program? So it is something that looks like this. Okay, so you want to minimize C transpose X, which what it basically means is C1 X1 plus so on up to Cn Xn, subject to a bunch of linear constraints that usually people write as matrices. So X is a vector, right? So remember, X is a vector of X1 through Xn. And B is also a vector, and A is a matrix. Okay, but if you expand it out, so it's like having m different constraints. So A is an m times n matrix. Okay, so you can think of it as A11 x1, A12 x2, plus A1n xn. Hopefully you can see that, less than or equal to B1, and A21 x1, 2n xn less than or equal to B2, and so on. And you have AM1 . So this is just some canonical way. I mean, this is the most general way you can write m constraints in n variables, all of which are linear. Right? So you have this matrix A which defines the constraints. You have the vector B which is the right hand sides, and you can write it succinctly as minimizing C transpose X subject to AX less than or equal to. So one thing to note is that once we are in linear programs, it doesn't matter if you are minimizing or maximizing. So why? For convex functions, I said it was very important that you can only minimize convex functions over convex functions. Right, but here I'm saying that it doesn't matter if you're minimizing or maximizing. Why is that? Yeah, so linear functions are in some sense convex and concave together. What that means is that minimizing C transpose X is like, maximizing C transpose X is like minimizing the negation of C. So you can think of C, we are not requiring C to be positive or anything. Okay, so you can just think of the negation, then you are just minimizing. So that's why with linear programs you could have maximization or minimization, and they're the same thing. And the second thing I wanted to say here, so this is the general form, this is how it looks like algebraically. But the nice thing about linear programs is that they have a geometry associated. And this geometric aspect is what leads to a lot of algorithms for it. So starting with the original simplex algorithm, everything that we know for linear programs kind of exploits the geometry of this. Okay. So you could of course apply a generic gradient descent type algorithm, but then we don't know of good parameters that make it converge. So what we try to make use of is the geometry. Okay, so that's the thing. And the first thing is, what is the feasible set? Right? So what do you guys think? You have a bunch of linear constraints. How would a feasible set look like? Yeah?
Hyperspace bounded by some hyperplanes.
Okay, so people don't usually call it hyperspace. Yeah, so you just think of it as a region that is bounded by hyperplanes. Okay, so I guess what you mean is just n-dimensional space. Yeah. So you have a region in n-dimensional space that is bounded by hyperplanes. Okay, so a hyperplane is something that looks like, I mean, you have n-dimensional space and you essentially have everybody on this side of it. So you have several planes in n-dimensional space. I'll give a concrete example of this in a bit, but this is roughly the picture that you'll have. Okay. So the way I would like to call it is that it's an intersection of half spaces. Okay, so it's of half spaces, and the reason is that, see, what is one single constraint? Right? A single constraint is saying that some linear function of the x's is less than or equal to something. Okay? So you will have ax equals b, a1x equals b1, let's say. This is the first constraint. And that is a plane. Okay, so that is a hyperplane. But a1x less than or equal to b1 is one of these regions. Right? It's either this region or the top region. So in this case, let's suppose it's the bottom region. So this essentially is a half space, right? So you have n-dimensional space. No matter where the plane is, things on one side of the plane is like half of the space. Right? So that's why this is called a half space. And what you have is an intersection of half spaces. So that's another way of thinking about it. Okay, so you have each constraint is a half space, and if you want to satisfy all the constraints, it's an intersection of all these. So that's and such an object is what we call a polytope. Is it always bounded? Yeah, not as we've written, right? Because you could have a feasible region that looks like this. So this whole thing, this infinite thing could be feasible. So good. So that's the geometry of linear programs. Okay, and just to give a concrete example, I wanted to draw a polytope in 2 dimensions. Right? So suppose you just have x1, x2. These are 2 variables. So n is 2. And I have a bunch of linear constraints. So a simple linear program here would be minimize x1 plus 2x2 subject to, let's say, x1 bigger than or equal to 0, x1 minus x2 bigger than or equal to 1. And maybe you have another constraint. So x1 plus x is less than or equal to 4. Okay, so these are just arbitrary ones that I just came up with. And now let's just see what the feasible set is, or the feasible set looks like, and how this optimization problem, what this optimization problem tries to do. So how do you start off drawing? So you have the plane, right? So you have set of all x1, x2s. What we've got to see is, so we know that each constraint is like a half plane now, right? So what is the first constraint? X1 bigger than 0, right? So what does it mean geometrically? Okay, so everything on this right, so x1 bigger than or equal to 0 is this whole space. Okay, so this region. Yeah, I'm going to mess up the picture anyway, so might as well do it from the start. Okay, so this is what we have, and yeah. So what's the second constraint? X1 minus x2 bigger than or equal to 1. And how does it look? Yeah.
x1 greater than 0 should be above the axis, right?
Above the x-axis?
Oh, sorry.
No, right? So these guys are bigger than 0. So yeah. And yeah, what is x1 minus x2 bigger than or equal to 1? So it's not very important, right? So, but let me try to get it right. Okay, so so usually write it as
1 plus 0 and 0
yeah, x2 and x1 minus 1. So is it below or
1 comma 0 and 0 comma minus 1.
Yeah. Oh, that's a good point. Yeah. So you have this and this line is in context. So this one and what's the other one?
0 comma minus 1.
This guy, right?
Yeah.
Okay. So you have this and top or bottom?
Top.
Okay. So I'm going to trust you guys. So this is the first two constraints. Okay, so the intersection of the first two constraints is this wedge.
It should be bottom.
Sorry?
It should be bottom.
So much. Okay, I think it's at this point easier to do this. So let's do that. Okay. So now you have x1 plus x2 less than or equal to 4. Okay. So this one I know how it looks. This one looks like this, right? Let's do it right. So this one looks like this. So the nice thing now is that the region that we are interested in, it's somehow this this yellow region. Right. So this is a nicely bounded convex thing. Okay. So this is how you typically draw these things, right? And so actually, interestingly, once you're in high dimensions, drawing these pictures becomes extremely complicated. Okay. So there's interesting fact that if you have you could have exponential in d many things. Like here, if you have n such constraints, or maybe m such constraints, then you could have something like m to the d over 2 many. I mean, the region could have complexities like m to the d over 2. Okay, so usually you get exponential in d complexity for this region. Okay, so in this case, the region is just a nice looking triangle. But in high dimensions, you could have lots of corners for this region. So, all right. So that's this, right? And now, how do I minimize a linear function, this x1 plus 2x2? So here again, as I was saying, you can draw level sets, right? So you can say x1 plus 2x2 equals 1. That will be some function that looks like this, perhaps. And equals 2 will look like this, and so on. Now you want to minimize it, right? So you keep drawing these level sets, move it until you get to the bottom. So what you realize is that then you can say that, okay, so this is where this x1 plus 2x2 is minimized. So actually, yeah, so this is kind of useful to know. So yeah, any question on what I'm doing here? I'm trying to see how a level set for x1 plus 2x2 looks like. Actually, what is a level set?
Contours.
Okay, it's related to contour. Yeah, it's actually exactly like contours. So a level set is basically the set of all points where x1 plus x2 is a certain value. Okay. So suppose I told you x1 plus x2 equals 5. That will be some set that looks like, that will be this line. And if I told you what is x1 plus x2 equals 4, this will look something like this. And as you decrease the right side, this thing keeps moving down. And essentially that's what we want to do, right? We want to minimize x1 plus 2x2. So we want to bring this line as low as possible. Okay, and it will be moving parallel to itself. And if you have this geometric intuition, then essentially this point minimizes the function x1 plus 2x2. Okay, so you're moving this x1 plus 2x2 equals c line, you're decreasing the c. So this is the geometric view of this. And the geometric view automatically tells you something pretty powerful. Okay, just that if you have any linear optimization problem like this, a linear programming problem like this, your feasible set, I said, is a polytope. It's an intersection of a bunch of half spaces. Right? So it could be a more complicated polytope, looks something like this. And to minimize, what we are doing is we are taking some plane and we are moving it all the way down or all the way up, something like that. Right? So what does it tell you about where the optimum should lie? Yeah, so one important fact about linear optimization is that the optimum is always attained at corner points. Okay, this is a key fact that we often use in linear programs. That because you have an object that looks that's defined by linear constraints, and now you're moving a hyperplane and you're looking at the corner. Now you could say, okay, what happens if my hyperplane was parallel to one of these things? Okay, and then I move it to the right, and then this whole region is now optimal. Right? But that's fine, because all we are saying is that, I mean, in some sense, there exists a corner that achieves optimum. Okay, so that's so you can look at this corner and that will be an optimum. Okay. So this is not saying that all optimals are corner points, but it's saying that there exists a corner point as well. And but for most directions, the optimum will actually literally be a corner point. Okay, because these are the only kind of degenerate cases where the optimum could coincide. I mean, where one face of the polytope could actually be the optimum. Okay, so any questions on this? Alright, so that's basic linear programming. Okay, so we know that all optima are attained here. Okay, so now we have an algorithm, right? So we have a candidate algorithm for solving linear programs, which is find all corners. Okay. Evaluate objective function at each of them. Okay, so candidate algorithm. Yeah. So it's evaluate function at each of them and return minimum. Okay. So can you guys think how you would implement this algorithm? I mean, these two steps are straightforward, right? So you can evaluate function at each given a point. How do you find all the corners?
Solve.
Yeah, so what you'll observe is that every corner point is the intersection, at least in this simple example, is the intersection of two of these planes. Okay. So in high dimensions, any corner point is, so this would be, what we know is that any corner point is the intersection of precisely n of the constraint equation. Okay, so you can enumerate, you can look at any n of the equations, try to see if you can solve them. Okay, so and that is a candidate corner. So are all such things corners? Is the intersection of any two things candidate corner? I mean, is it actually a corner point of the polygon? Yeah, so you can, it doesn't have to be, right? Like even in a plane, think of these two equations and then there's another constraint like this. And let's say this is the object and this is the feasible region. Then if I take these two equations, they intersect at this point. This point is not in the polygon. But that can easily be verified. So what you can do is evaluate all the corners, candidate corners like this. See if that guy satisfies all the other equations. Then you know if it's actually a corner point or not. So that's how you can, so this is a reasonable algorithm. There's one problem with it. So let's see what could be a serious issue with it.
Higher dimension, it's very difficult to.
Good, that's one of the issues, right? So firstly, in high dimensions, in n dimensions, this takes n to the m to the n time. You write m choose n time. Okay, because you have m equations, you've got to select n of them each time. What's another, some sense more fundamental problem?
If I have more variable than the number of equations, suppose if I have x1 to n, but I have only 2 or 3 equations or relation, then I can solve the equation.
Yes, and what is that geometrically saying?
We don't have a proper
so,
bound on the.
So the feasible set could be infinite.
Feasible.
So that's another way to say this. Another issue for this algorithm. Okay, so that the feasible set can be unbounded.
Will you explain the first one again? And dimension is m choose n because you're choosing n.
Yeah, you have m constraints.
Yeah.
Of those, you're choosing n of them each time.
And you don't know which of the choices.
Yeah, you don't know which
So you have to try
you
all.
essentially have to try all. So that's at least how I've written this algorithm.
Okay.
So, right. So these are the two problems with this sort of an algorithm. Okay, so this problem turns out to be not too serious. Okay, so there are ways of dealing with this. As such, it is a problem. Okay, so you have ways of dealing with this. So you can assume for now that all the feasible sets are bounded. Let's say. Okay. So let's assume for now that all feasible sets are bounded. So even so, this is prohibitive, right? So this is m choose n time, which is exponentially n. So this is what the simplex algorithm tries to kind of circumvent. So what it says is you start with one vertex. Okay, very often finding one vertex is kind of easy. You solve a bunch of equations, hopefully it's feasible, and then you will find one point. Okay, so actually it's not very obvious. I mean, even this, in fact, if you want to be completely theoretical about it, it is known that finding one feasible point is as difficult as solving the whole. Okay, so in fact, you guys can, I don't know if I should make it a homework, but you guys can think of it yourself, because in some sense, you can encode the objective function as a constraint, and you can ask for different values of the objective function. then you are essentially checking feasibility. So in some sense, it's not, I mean, finding one point, finding the starting vertex could be a challenging problem, but in most applications, finding one point turns out to be easy. Okay, so you start with some vertex that you know is a corner. Or you start with some point that's inside and you start moving towards the corners, see where you hit different things. Okay, so there are ways of doing this. So what the simplex algorithm does is starts with one vertex of the polytope, then it just keeps, and now it computes all its possible neighbors. Okay, so if you have one vertex, you know what all are the planes that intersect it. So you keep n minus 1 of the planes the same, then you change the other plane, then you hope that you move to the next vertex. So again, how we do this is not terribly important. Just picture geometrically that there is some procedure of moving of finding all the neighbors. And so what it does is, you have one point, you see what are all the neighbors of this, and you move to one of them. And how do you pick which one to move? Any guesses?
Nearest.
Best improvement.
Could go to the nearest, but maybe it versus, well, yeah. So more obvious thing is just, I move to the one where the objective function is as low as possible. Okay. So, and you stop when none of your neighbors have an objective function that's less than you. Turns out that is actually this is a simple consequence of this local optimality thing that we spoke about for convex functions. So it turns out that if you can't move to one of your neighbors and improve your solution, then you're actually at an optimum. And this is actually relatively simple, but I don't want to prove it. You guys can actually, if you want to think about, play with it for a bit, you'll probably realize why it's true. Okay, so yeah, but I just wanted to outline what the algorithm is. Okay. So this is what it does. Okay, so it just finds a start vertex and it goes to the point that minimizes the object. And the interesting thing is that this algorithm works really, really well in practice. Okay, so in fact, for a long time, people thought that this was polynomial until somebody came up with a counterexample where it could take something like 2 to the root d time. Okay, so it's again a weird thing that it's non-standard running time. Okay, so they could root n in this case. Now, number of dimensions is n, so it could take exponential root n. So there are examples like this. This is called the Clementi cube. It's a weird object that happens to happen for which you would take exponential time. Yeah.
But then we cannot say that it is polynomial. I mean,
in general, this is not polynomial
because exist such
corner
cases.
Yeah. So there exist some bad cases where you could actually take exponential. So that's why this algorithm, it's nice in practice, but we don't have we don't have good theoretical guarantees for this. So right, so this is what I wanted to say about this. And so there is this ellipse, there is this Katian's algorithm, as I said, which is provably polynomial time. Okay, so where and here there's a huge industry around this. Okay, so a lot of people have studied. Okay, what if I pick my neighbor carefully instead of going to the neighbor that minimizes the objective function? Okay, so there it's actually an open problem. Okay, so it's actually one very big open problem in geometry is what is called the Hirsch conjecture. And what it says is that the diameter of any polynomial is of any polytope is polynomial in the dimension. Okay, so that's like saying given any 2 points on a polytope in n dimensions, there is a path from one point to the other just following these corners, such that the length of the path is at most polynomial in n. And we don't know counterexamples to this. People widely believe that this is true, but there is no proof. And Yeah, in fact it was embarrassing. Until recently, no one knew that it was not more than n. And recently somebody came up with an example that was 2n. Okay, so we know that that is false. But we don't know that it's not n squared. Okay. So, yeah, so this is what is called the Hersh conjecture. Yeah, this is just to illustrate that even basic problems about polytopes could be pretty difficult. Okay, so this reason, so this is by Kachian's algorithm. This is the one that's the first, this is a Russian algorithm. So this takes a different viewpoint. Instead of moving through the corners, it moves through the polytope. You might think this is a natural idea, but people had no idea how to analyze these kind of things. Okay, and that's what Kachian does. And these are what are called interior point methods. What you do is you kind of move slowly through the polytope and reach the object. So, yeah, so these are what are called interior point methods. But the bottom line which you should remember is that linear programs can be solved in polynomial time. Okay? In practice, even simplex algorithm work great, but even theoretically we know this Kachian's algorithm and a lot of other algorithms afterwards that work in polynomial time. Okay. Alright, so that's basics of how you solve linear programs. So now let's go to what is more the focus of the course, which is we have this black box, right, which is, I have a fast algorithm for solving linear programs. How do we use it algorithmically? So that's what we want to understand. Okay, so we think of linear programming as a tool. So you have this thing that you can solve, optimization problem that you can solve efficiently. We want to reduce, we want to phrase various problems we have as such optimization. So let's look at a simple example of max flow. Okay, so we all know max flow. You have source, you have sink, you have a graph with some capacities. Okay, so capacity is 1, 2, something like this. We want to send as much flow as possible from S to T. So the goal is send as much flow as possible. While respecting all capacity constraints. So, how could you possibly phrase this as a linear program? So remember I mean it's been a while since we've done flows and unfortunately there was no homework on flows. But you know, I mean we saw two views of flows, right? So one of the things was you try to say, okay, I send some flow along this path, some flow along this path and so on. You have you have a bunch of paths and that defines a flow. And then we also had this viewpoint of, you can think of a flow as flow on every edge. Then we said that essentially you had to satisfy this flow in equals flow out, which is what we call flow conservation at every vertex. So which viewpoint do you think is more reasonable for linear programming? Yeah, the second one seems natural, right? Because what you have is, you have variables which are flows on every edge. So what you can say is, I have all these capacities, let's call capacity on edge. E is C sub E. And these are known constants. And all you can say now is I have of Fe, flow on edge T. And yeah, so what are now the constraints?
FE is less than equal to C.
Okay, so Fe is of course less than or equal to Ce because flow is always at most capacity. What else?
Each vertex sum of incoming flow should be equal to outgoing.
Yeah, so for every vertex, you know that which is not the source of the sink, you know that the flow is conserved. Okay? So the total incoming flow equals the total outgoing. Okay, so for all u not equal to S not in ST, we have sum over so this is E in incoming to the Fe equals sum over E going out of and this is just basic flow conservation. Right? So sum of all the flows on the edges coming into U is equal to the sum of flows on edges going out of U. And this is flow conservation. And what is the objective? Yeah, you want to maximize something, but what?
Flow out of the source.
Yeah, flow from source to sink is what you want to maximize, but we know that along everything else it's conserved, so flow out of S is essentially the flow that's going. So it's max sum over, I mean, just for technical reasons, because you could have flow going into S as well, you're going to say flow coming out of S minus flow coming into S. So sum over E out of F minus sum over E into U. Yeah, because otherwise you could just unnecessarily have a cycle and have a seemingly higher flow. So it's the net flow out of S that you want to maximize. Okay, so this is net flow out. Okay, so this is what we want to maximize, right? So now, so note that this is just, I mean, these are all just linear constraints. There's nothing fancy that we've done here. And there's no integer constraints, nothing. F's are allowed to be arbitrary real numbers. So this is in some sense the quintessential application of linear programming, right? So it's, you've cast the problem precisely as a linear program. So in fact, you know, this is the reason, like we've been debating whether to even do flows in this course, because flows are just linear programs. So if you do linear programs, you don't have to come up with new algorithms for flows. Okay. But it turns out the algorithms for flows are nice in their own sense. They're a bit faster than using these black box linear programming solvers. But in practice, you know, some people use these kind of algorithms for flows. Okay, because just throw it to a linear programming solver, it will just immediately solve it. Okay, so there are very fast linear programming solvers known. So if you don't want to code up a flow algorithm, you could just say, okay, yeah, just solve it, right? Give it to a solver. Okay? So that's one of the nice things about flow. Okay. And so the other thing I wanted to give an example of. So this is actually a bit more non-trivial. Okay? So it is bipartite matching. Okay, remember, so this is a problem we keep seeing, right? So this is like the Santa Claus type problem, where you want to give gifts. Gifts and children. You want to give one gift to each child.
Don't we frame this one like a flow problem?
Yes, you could phrase it as a flow problem, but if you remember, you could phrase it as a flow problem only if there were no
Zero.
weights. Yeah, 0, 1 weights. Okay, so that's exactly what we will come to. Okay, so we'll now say that in this viewpoint you can get rid of that restriction. So yeah, so I was hoping somebody would remember that. Thanks. So all right, so okay, so the problem itself, you have gifts, children. Each child has some happiness for a gift. Okay, so this was Wij. And you want to make an assignment so that want to find an assignment. Find an assignment so that the sum of the weights of the things you've assigned is as large as possible. So yeah, so meanwhile while this is charging, what would be the variables here? How would you want to write? Cast this problem as a linear program. You want to somehow encode an assignment, like I maps to j kind of.
So we can write xij.
Okay, so you want to write xij. This is supposed to be what? Supposed to be 1f you assign.
Gift I goes to child j.
Yeah, this is supposed to indicate if gift I goes to child j, right? But what kind of a variable? What values do you want it to take?
Happiness.
Oh, you want to take. Okay, so you want it to be 0 if you assign, and wij if you don't, or wij if you assign, and 0 otherwise.
Or we could take 1.
Okay, so it turns out mathematically more elegant thing is to say, okay, it's 0, 1, then I will multiply the xij with wij. Okay, because wij's are known constants, I don't really have to. And yeah, the whole thing becomes nicer if you do it this way. So, alright, so this is a 0, 1 random variable. Sorry, not random, this is a 0, 1 variable. And, alright, so xi is supposed to be, if you assign I to j, and 0 otherwise. So what are the constraints? So this is already looking a bit problematic, right? Because we already said you can't optimize over 0 on things. But let's first write the constraints at least. Okay, so what are the constraints?
Yeah. So sum over xik, where k varies over quotient should be less than equal to 1.
Yeah, so you're saying
Should
xi
be exactly
1
1 actually.
yeah, so 1 up to xi, let's assume there are n gifts and children, xin equals 1. This is true for all I. Saying every gift is assigned to precisely one child. So, good. And what else? Sorry? Yeah. So even the other way around, right? So this, if you had only these constraints, you could have assigned all the gifts to one child, which you don't want, right? So you want to say that, okay, yeah, for all j, x1j plus x2j, xnj equals 1. So these are the natural constraints. And anything else? So far, it seems reasonable, right? So it's these are the constraints. And what is your objective function? You want to maximize the total weighted happiness, right? So
Sum of xij and
yeah, so this is just sum over all pairs, sum over all ij of wij times xij. The reason this is reasonable is because xij will be non-zero only if you have assigned it. So you will only count things, the happiness value of things where you actually assign. So that's why you have this. This is the objective, and these are the constraints. But we still have this problem, right? So we want xij to be 0 or 1. So this is where we'll see the first example of what we call convexification. Okay. So we just boldly remove this constraint and replace it by 0 less than or equal to xij less than or equal to 1. Okay. So this is something very common in phrasing problems as convex optimization. You write down all your constraints, you have your variables that are probably supposed to be integers or whatever, and then you pretend that okay, I can't solve it over integers, so let's just try to replace these constraints over by 0 less than equal to xij. And in this case, turns out that this is actually not a problem. Okay, it's kind of a non-trivial fact, but it turns out that solving this program has this nice property that, or rather, if I look at the feasible set, right? So the feasible set is just defined by these guys and this. The objective is an objective function. So it turns out the feasible set has this very cool property that all the corner points of the feasible set are integers, are integral points. They are integral in the sense that xij are either 0 or 1. So this is a rather surprising fact, right? So remember, here you have n squared variables and so on. So if I have these n squared variables, I have these bunch of constraints. And what this says is that if I take any corner point of this feasible set, it's actually an integer point. And it turns out this is actually not very easy to prove, so we won't prove it. But if you believe this fact, then essentially what you're saying is that you can solve this weighted problem just using linear programming. Right? Because you have this, you write this linear program, this just has like it has 2n constraints or whatever, and you have these xij non-zero 10 constraints as well. And you are maximizing this linear function over this feasible set. And the nice thing is that you will always get a corner point. So you will get some corner point, and this result which we have not proved, so this turns out to be a theorem. Actually, I don't remember who proved it first, but yeah. So this turns out to be true, that all the corner points of this feasible set are integral. And by this theorem, once you get a maximizer that's a corner point, you're done. Because then we know that any integer solution corresponds to a true assignment. So so this is one non-trivial example of how, yeah. So all right. So this is the example of bipoint exponential. So maybe we have a little bit of time. So I want to say something about motivated for next class. Okay, that somehow this is a very lucky situation. Okay, that you have a feasible set and it somehow holds that the optimum is that every corner point is actually an integer point. Okay, so this is kind of rare. So usually once you relax, so this is called relaxation. Okay, so once you remove these 0, 1 constraints, replace them with xi less than or equal to 1, turns out your feasible set grows, and it grows in kind of an unpredictable way, that you will have lots of other corner points that are fractional. So we'll see an example of this now. And then the question becomes, how do you deal with these corner points? Suppose you optimize and you get to a corner point, what do you do now? So let's take the independent, so again, as you would suspect, we should try to write such a thing for an NP-hard problem. Right? Then we know that it's going to fail. Okay, so that's why we look at independent set. Okay, so last time we wrote constraints for it, right? So you have xi, xu for every vertex, and we said that xu, this is supposed to be 0 or 1, and the constraints are for all edges uv, xu plus xv is less than or equal to 1. And this is a pretty nice linear program, right? So this is, and now suppose you try to follow this previous philosophy, saying I'm going to drop these constraints and just say xu lies between 0 and 1. And your goal is to maximize sum over u xu. So this is now a pretty simple linear program, right? So you're saying maximize this subject to these constraints. So these are, each one is a linear constraint, and you're just maximizing some linear function over that. And this problem you can solve. And this better not always give you the solution to the integer thing, because then you will be able to solve independent set efficiently. Okay, so what's the catch here? So let's see what these kind of things can do. So I'll just draw this example and let you figure it out. So let's suppose that the graph is just like this. Okay, so you have UVW and you have this. Then what this program tells you is that firstly, what is the maximum independent set size in this graph? This 3 vertices? 1, right? You can't, no matter which two you pick, there's an edge. So the maximum independent set size is max is equal to 1. But now suppose I just want to satisfy these constraints, right? So the constraints are just xu, xv, w, xw, they are all in 0, 1. And you want xu plus xv less than 1, v plus xw less than 1. Can you think of an assignment where all of these are less than or equal to 1? I mean, all these conditions are satisfied, but sum of xu is actually more than 1.
Increasing to half.
Yeah, so you can set everything to half. Okay, and this will always satisfy this constraint. Okay, so you can just say all xu equals half, and then xu plus xv plus xw is 3 by 2. So the linear program has objective optimum that's 3 by 2, but the actual independent set is only 1. And now you are beginning to think, okay, so what, I mean, in some sense, what does half even mean, right? So it's like, so for independent set, it turns out this is a pretty useless solution. In fact, like you can have a clique on n vertices, okay, and like all possible pairs of edges are there. Here the true independent set value is just 1, because you can't pick more than one vertex. But this thing, optimization problem, will have value that's n by 2. You can again pick the all half solution. So this is kind of a problem for which this way of formulation kind of fails very miserably. Okay, so it's you can't say anything meaningful. You can't get anything meaningful out of replacing the 0-1 constraints with just this xu less than 0. So this is like a very bad example, and what we saw earlier was a very good example where removing those 0-1 constraints, replacing them by this actually lost you nothing. Right? So you preserved the original problem. And here it kind of essentially lost you everything, right? So you get this meaningless solution. Okay. So yeah, so next time we'll see problems in between and kind of see how you get interesting answers from